Hello, everyone. Today we're going to talk about forces. This is part two of mechanics and Xhyn physics. Well, as we know, force is tremendously important in physics because it's found everywhere. Everything moves, everything functions due to forces, due to fields, due to particles throughout space, which generates our reality, which generates space-time, which regulates the flow of time, which regulates the motion of objects through space. It's all a product of the presence of forces, which is a result of there being a field. There are fields that are generated by particles, such as weak, strong electromagnetism, and there are fields which are generated by some unknown phenomena, such as gravity. A force is a push or pull which can lead to changes in an object's motion. It is measured in newtons and it is equal to mass times acceleration, F equals ma. Example 1. In the figure above, there are two equal forces acting on a star in opposite directions. This means that the acceleration is zero and that the star will either remain at rest or move at a constant velocity. This is Newton's first law of motion. If the net force is zero, the object will either remain at rest if it's not moving or move at a constant velocity. Example 2. In the figure above, the net force is to the right, leading to an acceleration. If at rest, the star will move right. If moving right, the star will speed up. If moving left, the star will slow down. If the force is in the same acceleration as the motion, the object will speed up. If the force is out in the opposite direction as motion, the object will slow down. If the object is not moving, whichever way the force points, the object will accelerate in that direction. Vectors are numbers with direction, so vectors have both magnitude and direction. Example of vectors are forces, velocity, acceleration, displacement, weight. Weight is the force of gravity on an object, so it is a force, it has magnitude and direction. The weight that we experience, the force of gravity that we experience, is towards the center of the Earth. Scalars are numbers only. Examples of scalars are temperature, speed, distance, and mass. You don't say it's 32 degrees Fahrenheit to the right. No, there's no direction and temperature. Speed is like velocity, but without direction. When we try to describe an orbit of a planet around the sun, the velocity of the planet keeps changing because the planet changes direction through in the orbit. But the speed can be the same because it's just magnitude. Distance travel, it's how far you go, not how displaced you are. Displacement is where you end compared to where you started. And mass is also a scalar because mass is the amount of matter in an object. It's not the force of gravity, but it's the amount of matter in an object. The sum of the forces acting on an object is equal to the net force. So here we got F1 and F2. So the net force here will be F1 minus F2, and acceleration will be net force divided by the mass. And we get the acceleration because F equals ma, F over m gives you a. So here we have an example of four forces around this star. F3 pointing up, F4 pointing down, F2 pointing to the left, F1 pointing to the right. So what we do is we add up the forces in the x direction, so F1 minus F2. We add up the forces in the y direction, F3 minus F4. And then depending on what the result is, we can find the net force, which will be a combination of x and y components. In this first example, the net force is right and up because the sum of the x forces gave us a positive result for x, which means x is to the right, and our sum of the y forces gave us a positive result for y, which means sum of y is up. Now, if the sum of the x forces is negative, the object will be pointing left, and if the sum of the y force is still positive, the object will point up, and the object will go left and up. If the sum of the y forces is negative, and the sum of the x forces is positive, the object will go down and to the right. If the sum of the x forces is negative, but the sum of the y forces is also negative, the object will go left and down. And of course, there's a way for you to use Pythagorean theorem and inverse tangent, inverse sine, or inverse cosine to figure out the distance or the direction of the net force with respect to the positive x-axis. And of course, the object could just have a net force to the right, left, up, and down. Velocity and acceleration vectors. When velocity and acceleration point in the same direction, the object speeds up. When velocity and acceleration point in opposite directions, the object slows down. When the object is not moving, any acceleration will cause the object to speed up. When a box is at rest over a surface, these are its forces. So you got the weight pulling down on the box, and you have the normal force pushing up on the box. The normal force is the force of the ground on the box. Because if there's no force on the ground, the box will go right through the earth into towards the center of the earth. But that's not what happens because there's something on the way. In this case, it's the ground. The normal force is equal to the weight so that the net force can be zero and the object can stay at rest. When a force attempts to move the box, but it remains at rest, the force is equal to static friction. The net force is zero. So static friction is the force present when the object is not moving, but a force is being exerted. If no force is being exerted on the object to trying to move it, then static friction is zero. But if there is a force acting on the object, but the object is not moving, the force is equal to the force of friction, which in this case will be static friction. Static friction is present when when a force is applied on an object at rest, but not enough to move it. When the object is moving, the friction present is kinetic friction. So when the object is then finally moving, the type of friction present is the kinetic friction. When the force applied is equal to kinetic friction, the object moves at a constant velocity. So if the force applied and the force of friction is the same and the object is moving, the acceleration will be zero, so it means net force will be zero, and the object will move at a constant rate. Newton's first law, of course. When pulling the box at an angle, the normal force and friction decreases since the object is slightly lifted off the ground. So if you lift the object slightly up in the direction upward or whatever, decreasing the normal force will be less because the components of the force that you're pulling perpendicular to the normal force will add up to equal the weight, and that can only be done if the normal force decreases. Normal force is equal to the weight minus F sine of theta. Why sine? Because sine will give you the vertical component of the force in the same direction as the normal force. Friction is equal to the coefficient of friction times normal force. Coefficient of friction can be static or kinetic, depending. Static if the object is not moving, kinetic if the object is already moving. And the coefficient of static friction is a coefficient of static friction when the object is about to start moving. It's at the max static friction is when we go over the max static friction, that's when the object starts moving. So we always base off that. Net force is equal to F cosine theta minus friction. Why cosine? Because it's the component of the force you're pulling that is parallel to the surface. Minus friction because that's the force in the other way. When pushing the box at an angle, the normal force and friction increase since the object is pressing stronger on the ground. Yeah, because if you're pulling down, if you're pushing down on the box, the force of the ground on the box will be greater. So that will increase friction. That will not change the coefficient because the coefficient of friction depends on which two surfaces are rubbing against each other. In this case, the box and the ground. So it will not depend on the coefficient of friction, but will depend on the normal force, which because the normal force will be greater, friction will be greater as well. Normal force is equal, it's the same equation except that instead of subtracting F sine of theta, we're going to add. because we are increasing the normal force there. And the equation for net force is the same because the parallel direction of the force is still going to be the adjacent side of that triangle, which will be cosine. Now, the outward machine is a perfect system to describe forces. If the masses on both sides are the same, the system does not accelerate. This is an ideal case where friction and moment of inertia are ignored. The outward machine doesn't exist. A lot of things we do in physics don't really exist. Are just ideal cases. They're useful for us to make some sense of the world around us, but we don't technically know what they mean. Um, we don't know everything, right? Science is a language created by humans, by scientists, in order to make sense of the unknown. And we're able to make predictions, and we're able to be close to the right answer. So we create ideal cases to help us visualize a system that doesn't exist, but even though the system doesn't exist, it's useful to understand concepts in physics. So if we now assume that the mass on the left is heavier than the mass on the right, the net force will be the weight of the one on the left minus the weight of the one on the right. So m1g minus m2g, right? Because these are the forces. The force of gravity is what's going to cause the system to move. The acceleration will be the net force over total mass, which gives us acceleration in units of meters per second squared. Now the tension, because it's an outward machine, we assume that the tension on both sides will be the same. So if you get the heavier mass and multiply times the gravity minus the acceleration of the system, you get the tension based off the heavier mass. You can also get the tension based off the lower mass by doing the acceleration due to gravity plus A. Where did this equation comes from? It comes from the fact that tension pushes up on M1 and weight pushes down on A1. So tension minus the weight 1 gives you the net force on M1. The net force on M1 will be negative because M1 will be going down. But so negative MA equals to tension minus weight 1. And then you solve this equation for tension and you get